guys, welcome to lesson 11.3, day 3. The vocabulary, there's quite a few terms in the vocab, which again you'll see on the answer key that I'm going to post. Rather than writing all of them down and drawing diagrams for each one, I'm just going to draw one diagram and explain each term within the one diagram. Okay, so here we have a polygon and it's inside of a circle. So the first term says center of a regular polygon. First off, that word regular. When we talk about a regular polygon, do you guys remember what that means? Regular polygon, because that keyword regular is important. Hopefully you guys remember that that means it is both equilateral and equiangular. So all the sides are congruent and all the angles are congruent. And I didn't do the best job drawing a regular polygon, but envision that this is regular where all the sides are congruent and all of the angles are congruent as well. All right. And just kind of as a quick recap, because some old information is going to be coming up in this lesson, if I wanted to find out what all of these angles add up to, there is a formula, the sum of the interior angles of a regular polygon, and that formula is n minus 2 times 180. That's going to be the sum of all the inside angles. Now, if I just wanted to know what one of the angles is equal to, we use this formula, but then divide by n. So n minus 2 times 180 divided by n, and that's for each interior angle. Okay, so that information is going to be helpful for some of these problems that we're going to be working on. All right, so center of a regular polygon. The center of a polygon's circumscribed circle. So if you have a polygon, which we have here, and then we draw a circle around the polygon, the center of the circle will be the same as the center of the polygon. So that's what the first term means. All right, then it says the radius of a regular polygon. The radius of a polygon's circumcentered circle. So again, if we have a circle, if I go from the center to any point on the outside of the circle, that would be the radius of the circle. But if we want to look at the radius of the polygon, we want to make sure, again, you're starting at that center, but then you're going to go to one of the vertices because the vertex of the polygon is on the outside of the circle. So if I draw a segment there, that is your radius. Okay, and I could draw a radius to this vertex or to that one or to, it doesn't matter, right? They're all going to be the radius of the polygon, which is also the radius of the circle. Then we have this thing called apothem. All right, the apothem is the distance from the center to any side of the regular polygon. So if I want to know what is the distance from the center to any side of the polygon, I'm going to draw, and I'm going to go down, straight down here, but I could go up, I go to this side. I'm going to drop a segment, and that segment is going to drop straight down. It's going to be perpendicular to that side. This is the apothem. Little a is apothem. All right, this shows the distance from the center of the polygon to the outside of the polygon. Now, the apothem does a few things. I already mentioned it's perpendicular to the side. It also bisects this side. So that's important to know, okay? This side is going to be bisected. It's going to be cut in half. It also bisects, if I was to extend it all the way down, it also bisects the arc. So let's say the arc measurement is given. You can divide it by 2 if the apothem goes all the way down, right? It bisects the arc. One other thing it does, if I was to draw the other radius, the apothem bisects this vertex angle here. Okay, so whatever the measure of that angle is, I can divide by 2, and that's the measure of that angle and that angle. So those are all little key important pieces of information we're going to be using. All right. And finally, central angle of a regular polygon, an angle formed by 2 radii drawn to consecutive vertices. So actually I already drew one. This right here would be your central angle because we have one radius and the other, which goes to the consecutive interior angle, that is called the central angle of the polygon. Okay. All right, so with all that information, I'm also going to be talking about rhombuses and kites. Let me get that up on the board real fast. All right, so we're going to talk about the area of a rhombus and the area of a kite. So in your notes, it says the area of a rhombus or kite with diagonals D1 and D2 is equal to 1/2 D1 times D2. Okay. Now, a rhombus and a kite, rhombus and kite, they are both special types of quadrilaterals, which we studied quadrilaterals earlier. So since they are both special types of quadrilaterals, we can always use the area formula base times height, right? That'll work for all quadrilaterals. But depending on the information that's provided, that might not be the easiest formula to use. So another area formula that we're given today is that the area of a rhombus or a kite is equal to 1/2 D sub 1 times D sub 2. And D sub 1 and D sub 2 are the diagonals. Okay, so for a kite, the diagonals would be this segment here, that's one diagonal, and this segment here. So if I know those lengths, I can multiply them together and take 1/2. All right, and then for a rhombus, the diagonals there and there. So if I know those two lengths, I can multiply them together, divide by 1/2, and that'll give me the area of the rhombus. So don't forget, you could still do base times height if you're given the base and the height of the rhombus and the kite. But if you're given diagonals, you'll want to use that formula there. Okay, so that leads us into example 1 and 2. So I might have enough room to do them up here. So for example 1, you're given did my best. I don't think I did a very good job redrawing that diagram. All four sides are supposed to be congruent, and then you're given 7, 7. Oh, these are the 10s. I'm trying to figure out what's 10. Those are 10. Okay. So you're given that all the sides are 10. And then this one diagonal is 7. So if I want to use the area is equal to 1/2 D1 times D2, I have to figure out the other diagonal length. Okay? So we're going to be using Pythagorean theorem in order to find the other diagonal length. All right, so a squared plus b squared equals c squared. A squared plus 7 squared equals 10 squared. All right, we're going to get 100, subtract 49 from it to get 51. So I have a squared plus 49 equals 100, subtract 49, a squared equals 51. So a is equal to the square root of 51. So I have square root of 51 and square root of 51. I'm going to leave it like that until I do my next calculation. So to find the area using 1/2 D1 D2, I have 1/2, diagonal 1 is 14 units long, and diagonal 2 is 2 times square root of 51. So I have 14, and then 2 times the square root of 51. For this type of problem, I would probably be telling you to leave your answer either in radical form or rounded to the nearest 10th or 100th. If it was in radical form, 1/2 of 14 is 7. Then multiplied by 2 would be 14 root 51. And I don't know if units were given. Oh, it is inches squared. Rounded to the nearest 100th is 99.98. So approximately 99.98 inches squared. Okay. All right, for problem 2. Problem 2, we have this kite. And you're given three, 2, 2, and 5. All right, so this time you are given all the diagonal lengths, so you don't have to do much math. You're just going to fill in. So the area is equal to 1/2 diagonal 1 times diagonal 2. Diagonal 1, 5 and 3 gives you 8. Diagonal 2, 2 and 2 gives you 4. So 1/2 times 8 times 4. Half of 8 is 4. And then 4 times 4 is 16. And the units were centimeters. And so it's 16 centimeters squared. Okay, so that is how you use those two formulas. Just keep on moving along. All right, the next problem, we're going to start using the area of a regular polygon formula. So that is 1/2 AP. Okay, that's the area formula for a regular polygon, where little a stands for apothem and P stands for perimeter of base. All right. Or we'll just say actually perimeter. When we get into our 3-dimensional shapes, then we'll say of base. We'll just say perimeter for now because there's only one shape. All right, so perimeter. So what we're going to do is the first problem says find the measure of a central angle of a regular polygon with 8 sides. Okay, so we have to envision a polygon with 8 sides. And we want to find one of the central angles. So the central angle, centers here, radius, right? I want to know what is this measure right here. Well, how many degrees are in a full circle? 360. How many central angles would I have if I was to draw all the radii in? Since this is regular, I missed one here. Since it is regular, all of the central angles have to be congruent. All right, and there would be 1, 2, 3, 4, 5, 6, 7, 8. It's an 8-sided figure. So you're going to take 360 and divide by 8 to figure out how many, or what the measure of each central angle would be, which would be 45 degrees. So each of these central angles is 45 degrees. All right. Problem 2 says the central angle of a regular polygon are 40 degrees. How many sides does a polygon have? Well, think about what we just said here. Okay. So this time they're giving you the measure of the central angle. They want to know the number of sides. Think about the relationship. This figure had 8 sides. I divided by 360 by 8 to figure out the central angle is 45 degrees. So the relationship would then be 360 divided by number of sides is equal to measure of central angle. All right, isn't that what we did here? So I don't know the number of sides for this problem. That's my unknown. I'll use n. but I'm given that the measure of the central angle is 40. Now here's my equation. I just have to solve for n. So you can multiply both sides by n, then divide by 40. You could set it up as a proportion. If you want to set it up as a proportion, put 40 over 1 and cross multiply. You have lots of options here. I'll just cross multiply since I set it up as a proportion. So 40n equals 360. Divide both sides by 40. And when you do so, divide by 40, divide by 40. Knock off the zeros, so it's really 36 divided by 4 to get 9. We're talking about a 9-sided figure. 9-sided figure has central angles that are 40 degrees. Okay, let's keep on working. Problem number 3. It says a regular pentagon has a radius of 4 inches and a side length of 3 inches. Find the apothem of the pentagon. Okay, so we have a regular pentagon, so a 5-sided figure with all sides and all angles congruent. Right, so let's draw our pentagon. Now, it's not going to look regular. The only pentagons I draw look like houses. All right, but we're going to indicate that all angles and all sides are congruent. That's why it's called regular. Okay, and if we want, we can draw a circle around this as well. There's the center. So my radius goes from the center to the vertex. My apothem goes from the center straight down, is perpendicular, and bisects that side. Okay. Now let's actually do what we did in the last problem. If this is a 5-sided figure, how many central angles are there? 5. Okay. So what is the measure of each central angle? Well, I can take 360 and divide by 5 to figure out the measure of each central angle. Okay. So, and I don't think that's one of the problems, but it might help us figure out some of the other pieces of information. All right, so 360 divided by 5, and then we'll divide that by 2, and I'll tell you that in a second. 360 divided by 5 gives you 72 degrees. All right, so that means if I was to draw the other radius in as well, this central angle is 72 degrees. Well, the apothem bisects that. So take 72 divided by 2, and you get 36 degrees. So this angle right here is 36. Now, why was that important? Because we're oftentimes going to do work with this triangle right here. Okay? 90 degrees, 36 degrees. So now I can figure out that missing angle right there. All right, so I'm going to do 180 minus 90 minus 90 minus 36 to get the missing angle down the bottom is 54. Okay. All right, so let's actually go back to what the problem was asking us to do. Even though I gave you lots of other good information that will be useful. The first problem set, or the directions say, a regular pentagon has a radius of 4 inches. So let's put in that radius length of 4 inches. And side lengths of 3 inches. So each of these sides, 3, 3, 3, 3. But instead of putting 3 here, maybe I break it in half, 1.5. And 1.5, because remember that apothem broke it in half. Okay. So it says, find the apothem of the pentagon. Well, with all that work I just did, do you guys now see the right triangle? 1.54. Can I use Pythagorean theorem to find the apothem? So the apothem squared plus a squared plus b squared equals c squared, right? Apothem squared plus b squared equals c squared. All right, so we'll work through that to get a squared plus 2.25 equals 16. Subtract 2.25 from both sides. So you have a squared is equal to 13.75. And then take the square root to get a is approximately 3.7 inches. So that's for part A of problem 3. Okay. Now for part B, the problem says find the area of the Pentagon. So let's try to use this formula. The area is equal to 1/2 AP. So 1/2 times the apothem, which we just found, 3.7, times the perimeter. Well, the perimeter, if each side is 3 and there are 5 sides, 3 plus 3 plus 3 plus 3 plus 3 gives you 15. And then when you multiply, you're going to get 27.81. And what are our units again? Inches squared. All right, guys, we have one last problem to work through. All right, for problem 4, I'm dropping everything, hold on. For problem 4, where am I? It says a regular hexagon has an apothem of 10 units. Okay, so let's draw a hexagon. Okay, so there's my hexagon. It's regular, so all sides and angles are congruent, and it has a apothem of 10 units. Okay, so again, let's talk about that central angle for a second. If I was to draw the 2 radii in and form that central angle right there, how many central angles would there be? It's a 6-sided figure, so 6 central angles. 360 divided by 6 gives you 60 degrees. So this central angle is 60 degrees, but the apothem bisects it, so it's 30 degrees. And if that angle's 30 and this angle's 90, I know that this angle has to be 60. It's a special 30, 60, 90 right triangle, which those are going to be coming up in this chapter as well. Let me get the glare off the screen there. All right, so I know the apothem. I know it's a 30, 60, 90 right triangle right there inside. What are we asked to find? It says find the radius of the hexagon and the length of one side. So I want to know what is the radius. I want to know that length. Well, that's where the 30, 60, 90 right triangles are going to come back into play. So just as a reminder, for 30, 60, 90, we know that the hypotenuse is equal to 2 times the short leg, and the long leg is equal to √3 times the short leg. Okay? The short leg is the one across from the 30. The long leg is across from the 60. So I don't know the short leg, but I know the long leg. Okay, so let's work backwards using this formula. Long leg, which is 10, is equal to √3 times the short leg. So to solve for the short leg, I'm going to divide both sides by √3. So I'm going to have 10 over √3 equals the short leg. I'm going to rationalize by multiplying top and bottom by √3. So I have 10 √3 over 3 is equal to the short leg. So this piece right here is 10 √3 over 3. Not the prettiest value, but that's okay. Now I need to find the hypotenuse by taking the short leg and multiplying by 2. So the hypotenuse is equal to 2 times short leg. The hypotenuse is equal to 2 times 10 root 3 over 3. So that's going to give me 20 root 3 over 3. So I have 20 root 3 over 3. So I now know my radius is equal to 20 root 3 over 3. But I still need to figure out one of my side lengths. If this piece is 10 root 3 over 3, and this piece is 10 root 3 over 3, I'm going to add them together. Or you're going to take 10 root 3 over 3 and multiply by 2. Okay? And when you do that, you're going to get 20 root 3 over 3. So your radius and your side length are the same. So it's 20 root 3 over 3. Again, 10 root 3 over 3, and this is also 10 root 3 over 3. I have to add them together, keep the denominator the same, add the numerators. 10 and 10 is where the 20 comes from, but the radicals don't get added. So that's where 20 root 3 over 3 comes from. All right? And finally, the last part is to find the area of the hexagon. So to find the area, we're going to be using that new formula. Area is equal to 1/2 apothem times perimeter. The apothem was given as 10, so that's easy. 1/2 times 10. The perimeter is a little more challenging, but not too bad. If each side is 20 root 3 over 3, then the perimeter is going to be 6 times that, because there are 6 sides. So the perimeter is equal to 6 times 20 root 3 over 3. You can cross simplify if you want. 3 goes into 3 once, 3 goes into 6 2 times. So that's going to give you 40 root 3. So that's what I plug in for perimeter, 40 root 3. So then I multiply. 1/2 of 10 is 5. 5 times 40 is going to be 200. So I'm going to have 200 root 3. What are my units? I lost my units. I don't know if they were even given. Nope, wasn't given. So we'll just say units squared. 200 root 3 units squared. If I was asked for a decimal approximation, it would be 346.41. All right. So I know that was a lot. That was a pretty heavy lesson. Give the homework a shot. Make sure you really watch the video and take notes. Slow it down if you need to. Shoot me an email if you're confused or have a question. And that's all for today. All right. Bye.